An oscilloscope does not show the absolute truth, it shows the response of the entire measurement system, the oscilloscope itself, the probe, the bandwidth, the sampling rate, and the trigger settings. That's why when debugging switch mode power supplies or high-speed digital signals, you may see ringing or voltage spikes that don't actually exist on the PCB. The opposite can also happen. Real transients are present, but the oscilloscope simply fails to capture them. The most common cause of false ringing is a poor probe setup, especially a long ground lead. The ground lead has parasitic inductance, while the probe and the oscilloscope input have their own capacitance. Together, they form a resonant LC circuit. As a result, when measuring a fast edge, the measurement system itself starts ringing. If replacing the long ground lead with a short ground spring dramatically changes the waveform, then you weren't measuring just the circuit. You were also measuring the parasitic effects introduced by the oscilloscope connection. But the probe isn't the only limitation. Oscilloscope bandwidth is just as important. Don't focus only on the interface clock frequency. Pay close attention to the signal rise time. A standard SPI interface may operate at only 10 to 20 MHz, yet its rise time can be just a few tenths of nanoseconds. FPGA interfaces QSPI and RMII signals often have even faster edges. If the oscilloscope bandwidth is too low, it will smooth the signal edges, underestimate voltage overshoot, and completely hide high-frequency noise. There are two more specifications that engineers sometimes overlook: sampling rate and memory depth. If there are too few samples across a signal edge, the oscilloscope begins reconstructing the waveform rather than displaying the actual signal. And if the memory depth is limited, increasing the time base forces the oscilloscope to reduce its sampling rate, causing short, infrequent transients to disappear from the screen altogether. That's why you shouldn't choose an oscilloscope based on the simple rule of more bandwidth is always better. Instead, choose one based on your measurement requirements. For relatively slow interface signals, an entry-level oscilloscope may be perfectly adequate. But when dealing with fast edges, intermittent faults, power integrity issues, or power electronics, bandwidth, sampling rate, memory depth, trigger performance, input noise, and a high-quality probe become far more important. Otherwise, your oscilloscope may either create problems that don't actually exist or hide the very problems you're trying to find. If you found this video useful, give it a like, subscribe to the channel, and check out our other videos on electronics design and hardware engineering.